You guys can hear me at home. Let's continue, all right? So, we are talking about a new part of chemistry, but nothing absolutely new. We have been talking about particle theory, mole theory. We've talked about building formulas, building chemical equations, balancing them. Law of conservation of mass is really huge in this area, as you are seeing. Okay, so using chemical reactions in our last couple of labs, we've been able to predict what we should get. In a couple of these labs, the experimental value should be almost dead on. Of course, there's always limitations. All right, so I hope I'm showing you through the labs and through the tests and all their assignments that a lot of this is very similar. So the chemical reactions that we're going to use in this area are no different. There's a limiting reagent, there's an excess chemical, there's stoichiometry involved, there's completion reactions. It's just there's some tiny specifics that may be new as I bring you on. So I'm bringing you into a new part of chemistry that is connected to all of the same stuff that we've been doing. So I'm bringing you to talk about acid-base chemistry, but we're still using chemical reactions, mole concepts, chemical formulas, stoichiometry. So it's really more of the same, but just in a different area, okay? So let's begin. So milk of magnesia, I don't know if you're aware, is something you may have seen or may have in your medicine cabinet. If you can see what it's made of, anyone can read that?
Magnesium hydroxide.
Okay, very good. Magnesium hydroxide. I thought I was in Catholic. I may have been in Mass just now. I believe in magnesium hydroxide. All guys came in. I don't think I know any prayers until we start chanting them together. Okay, it's like I need that first couple of words. We all go together. Like I got you. All right. So yeah, magnesium hydroxide. So what is magnesium hydroxide? Well, magnesium hydroxide is a chemical that we use for gentle, soothing relief for upset stomach and indigestion. Your little tummy is hurting. What's that?
And it's mint flavored.
And it might be mint flavored. We're not going to talk about the mint chemical. We're going to talk about the active ingredient. This is traditional mint. I don't know what non-traditional mint might be, but this is traditional mint. Okay. Hip hop mint coming next week. I'm not sure. All right. So what is, and of course, a competing chemical that actually would do the same thing is liquid Drano. This is something that you would not ingest, and this is something you definitely would. Okay, this cleans your drains. This would clean your esophagus and your stomach, but it would also lead to death and internal bleeding. But essentially, they're the same chemical. So now they're not the same, but they have the same chemistry. All right, so we're going to talk about today. So also talk about solubility. So let's talk about magnesium hydroxide. Okay, so magnesium hydroxide.
Where's your black marker?
Oh, I don't know. I was making some stuff up here. Let's go to here we go. So let's go to my slideshow to do this better. Okay, someone is. Where'd my phone go? Someone's talking to me. Could be someone home.
Near your mole box.
Under my mole. Thank you. Okay.
To the mole box.
It's my son in school, so.
Oh, I know where my mole box is.
He
He doesn't have a mailbox, he has a mole box.
All right. Darn right.
22.4.
Okay. So what we have here is magnesium hydroxide, MgOH2. Okay, you know magnesium likes to become +2. All right. And of course, hydroxide's -1. But let's just talk about the demo here. I've got a tall flask, like a tall person. And what I have inside here is a magnetic stirring bar. It's basically a metal rod with a plastic covering. And we've got a magnet that spins here, so this thing is going to spin this and help me dissolve. I'm going to throw in some water. Okay, I don't want to use that water, so give me a second. So let's throw some water in. Okay, as I spring to action to get this water, thus spring water, it's crystal geyser. Okay, it's a geyser of clear, I don't know. All right. So there's my crystal geyser water, H2O, and I'm going to spin it. Okay. Okay. Now, I'm going to add magnesium hydroxide Oh my gosh, chemicals! It's the same thing as this, but it's magnesium hydroxide. As we can see, it's 1 magnesium plus 2 with 2 hydroxides. Okay, and as we throw some stuff in here, we can wait till the cows come home to watch this dissolve, and we have an issue. It's not going to dissolve. It's an insoluble compound. So when you take milk of magnesia, they call it milk because it's a white precipitate, okay? Is it really a liquid? No, it's actually suspension. Suspension is, we've got crystal, okay? We've got crystalline powder of milk of magnesia suspended in water. You can't see through it, okay, because it's not a solution. Water cannot compete with those charges. And so what are we looking at here? Well, we're looking at the following, and it's weird. We drink the suspension? Absolutely. And my markers. So what do we have? We have Mg plus 2 attracting a hydroxide. Now, it's not really a 1-to-1 because there's 2 hydroxides per every magnesium ion. But I'm just going to draw this for simplistic case. We've got crystals. And what do we know? Well, based on Coulomb's law, for the millionth time, this plus 2 is so high in charge, guess what? Water can't compete for those charges, and that stays in a crystalline solid. So why in the world do we use it? Well, we know in our stomach, all right, if we have indigestion, most of the time it's because of an overproduction of hydrochloric acid. We have parietal cells in our stomach that produce hydrochloric acid, and for good reason. Number one, it kills all bacteria that goes into our stomach so that we're not carrying bacteria into our digestive tract, all right? And of course, we have bacteria that lives past in our large intestine that's helpful. It's probiotics, where we produce a base to neutralize that. But the bottom line is, we produce hydrochloric acid. That hydrochloric acid does a couple different things. Number one, it kills all bacteria that we ingest. 2, it helps break down proteins because it produces an acid, okay? Now, what are acids? And there are a couple of different definitions. But acids, generally speaking, okay, we're going to start this way and we'll define this, produce H pluses. Okay, very simple. The one that I've been using in class is hydrochloric acid. And it breaks apart into an H plus and a chloride ion. Now, I'm going to call this H plus a proton. We should know why it's a proton. Hydrogen has a mass of 1 and a proton of 1. We know that it's a proton, and it's got an electron on the outside. It has no neutrons because when you subtract the mass from the atomic number, you get 0. So if you're an H plus, you are a hydrogen atom without an electron, which leaves what? Just a proton. So you will hear me say, hey, this gives off protons. It is synonymous with H pluses. Now, something about Coulomb's law. Okay, and I have to write it because it's that important. The force of electrostatic attraction using some constant times the size of the positive charge, well, the amount of the positive charge times the amount of the negative charge all over the distance squared. Well, what do we know? Protons. My friends, when I say H plus, I don't really talk about a hydrogen as plus 1. In my mind, it's a proton. Isn't a proton a fraction of an atom? It's not an atom, it's part of a nucleus. All right? If you think about gold, okay, AU guys, atomic number 79. Gold's got 79 protons and it's got electrons. Hydrogen is just 1 proton. It's like a piece of a nucleus of most atoms. So this thing is what? Incredibly small, which means its distance, okay, between other ions when it has contact, or it's, if you think about distance squared, sometimes they use radius. Its actual radius is going to be really small. What's the force of attraction? Tremendously what? If your denominator gets smaller, the force of attraction is what? Tremendously high. I think of it as charge density. I'm putting all the positive in a small area. That's really positive 1. Why? Because all the positive in a small area can make other things feel that positive. If I was to stretch out +1 over a big radius. And if something comes in contact, I won't feel all of that +1. So think of it as charge density. That's you'll hear it by professors in college. Okay? So, getting back to acids, what do? They give off protons. Okay? And because they're tiny, obviously it's a piece of an atom, piece of a nucleus, all right? And because they're so small with a +1, they're a heat-sinking missile for electrons. They are really good at ripping electrons away. We know this because I added hydrochloric acid to metals. And what does it do to metals? It pulls electrons in metals and corrodes them. Okay, we know that. Now there are some metals that are not corrosive, okay? But Drano, we add to our drains, that's same kind of chemical, delivers the same chemical, but this would dissolve, okay? We use this to dissolve proteins or things stuck in our drain pipes. We would never pour hydrochloric acid down a sink to clear our pipes. It would work, but the problem is it would decay our what? Pipes. Okay, so we don't do that. So acids give off H+. Okay, now there's a competing scenario what a base is. A base, by simplistic terms, produces hydroxides, just like milk and magnesia. Now, what do we care? Why they're acid-base reactions? Because they work in unison. And first and foremost, you guys are going to talk about pH probably tomorrow. We care about how many of these are around in solution and how many of these are around in solution for good reason. When there's a high concentration of H+, when you have a tremendously acidic environment, pH is really low, life can't exist. And you know why life can't exist? Because these H+ will rip and break organic bonds. Okay, I'm going to explain that in a second. So when we have H+, because they're so positive. Now remember, being positive and very small makes your force of attraction, it's a tremendous oxidizing agent. It's going to rip electrons away from covalently bonded material. I'm going to show you that in a second. So this is dangerous. Okay, high amount of H+ are considered to be corrosive. The word corrosive means that the H+ in high concentration can break things down, can make metals become salts, produce hydrogen gas, can cut the bonds of things that are organically. Putting our body in acid will dissolve our body. It'll take time depending on the acid and the strength, but it can occur. Now, if you have too much of this, that's equally dangerous. We call that caustic. Caustic. Things with tremendously high hydroxide ions, guess what? Will also break down organic matter. Will also break bonds by doing it a different matter, and I'm going to show you that in a second today. They're caustic. They're dangerous. Life cannot exist if there's a lot of hydroxides around because that'll break bonds of organic molecules. They can't live. And if there's too many H+, they'll break down. So a high pH occurs, that we're going to learn. Low pH occurs when you have too much of these around, and that's usually bad because anything that's trying to use organic molecules to live, they'll be broken down before they can be used. If things are tremendously basic, that means that what? pH that's high, we'll talk about that, it's too caustic. So those chemicals, we better be aware how much we have in a solution. Now, what's interesting is that when you add them together, we have something called a neutralization reaction. Hey, who neutralizes things? You think about neutralization. Something strong can wipe away something else. Well, neutralization reactions are important. If I have a lot of H+, I can make that solution safe by neutralizing them. So for instance, if I have H+, which we know are dangerous, and I'm going to show you that, and I add them to hydroxides, what do you think it makes? Water. This is going to make H2O. Unless I'm missing something, H2O is not dangerous to us. This is called a neutralization reaction. Dangerous by itself in high concentrations. Dangerous by itself in high concentrations. Water is not dangerous to us. So that's an important part. And there's one of these to one of these. When we get to acid-base reactions, it is always about one proton to one hydroxide. That's the stoichiometry. Okay? Now, let's get back to milk of magnesia. Okay? All right, now, we've got this crystal. And we know why we have it, because in our stomach, we have something called parietal cells. Parietal cells produce in our stomach, there's my stomach, okay? This would go to the small intestine. I'm not sure what that little foot there is. Maybe it's a wing, it's an aerodynamic. But in any case, I've got H pluses in high concentration. What are they going to do? Well, if you don't already know, organic matter looks like this. It's carbon-based. And the bonds between organic matter are covalent. They have to share electrons. What do we know in the right-hand corner? Don't they attract electrons? They're good at pulling electrons. We talked about in redox, the upper right-hand quarter elements are so small, they attract their own electrons and they attract other people's. So these guys are fighting for electrons. So they're pulling on each other. And we learn that carbon, who has 4 valence electrons, shares a total of 4 more to become stable. So carbon starts with 4 valence electrons. And then the other elements that it's with donate their electrons, and carbon will make a bond by sharing those electrons. You notice where carbon is in the periodic table, it needs 4 more electrons to become as stable as a noble gas. Noble gases have filled energy shells. That was this summer. So carbon has 4 valence, 4 outermost. Because it's good at attracting, it'll attract 4 more and be forced to share. This is not an ion. Now, what does H plus do? If I have too many acids, H pluses are so small, heck, it's going to be like this. It's part of an atom. So small and positive, what's it going to do to these electrons? It's going to pull them. If you've got little H pluses that are so small, based on Coulomb's law, heat-sinking missiles, it's going to pull these electrons. And if you keep pulling these electrons, can you guess what happens to your bond? It breaks apart. And that's why acids are corrosive to organic matter. They're corrosive to metals because they'll pull electrons from metals and make them into ions and salts. That's why acids can break bonds. This was carbon double bonded to a carbon. I mean single bonded. A single bond's a pair. That's now broken. So that can go this way, and now it's broken down. Acids in high quantity are dangerous, okay, because of that. They're corrosive. All right. Now, what about hydroxides? Hydroxides are also corrosive. Let me give you an example of why, okay? You guys last year in EP Bio, let me give you a real organic piece of molecule. Remember amino acids? We had this guy right here, double bonded to an O. By the way, double bond is 4 pairs of electrons. So just think of these are pairs. Then we had this bonded to an N, who is bonded to an H. This is bonded to a C. This is an R group. This R group, of course, could be polar, non-polar. It changes the amino acid. Okay. And this would be an H here. And so the amino acid, this will be an N here. So the amino acid, the amine group is the N, and the acid group is this Q group. Now, this would be the start of another amino acid where we have an N bonded to a C, another R group that could be the same or different depending on the amino acid, to another C that's double bonded, and here. Now, we call these amino acids bonded to each other over and over again polypeptides. And this is a peptide bond. This is linking one amino acid to another. And this one would be to another peptide bond. Okay, what are found in the drains of your home? What clogs them up? Hair, mostly. If you're shaving, hair clogs them up. They're hairballs. We don't want to drop acid. We know acid will break those proteins up because the acid will pull the what? Electrons away from these bonds and break it up. But then it's going to get into your pipe system and possibly do what? Okay, cause your pipes to decompose. So we don't want to do that. We use Drano, but these are similar. Now, what does hydroxide do? Well, a hydroxide is a very important polyatomic ion. It's a oxygen, has 1, 2, 3, 4, 5, okay, 6 valence electrons. It needs 2 electrons to be stable. Hydrogen has 1. So to be stable, this thing needs 1 more electron, so it gets one from the environment, and we draw this. It's a polyatomic ion. Now we've seen this as the result of what? Oxidation, reduction of water. We've seen this. We produced hydroxides when calcium carbide took the H's off. This, if you notice, is a small ion. Okay, so it's small. Why? Oxygen is small, and so is hydrogen. So this is a really small ion. And the whole thing's -1. So being small and -1 makes it to have great force of attraction, but it's different. It doesn't attract electrons. Here's what it does. Check this out. So cool to understand the chemistry. We know that oxygen, compared to carbon, is better at pulling electrons. It's over to the right. Okay? And you may say, well, Mr. Grotsky, how do we know that? Okay? How do we know that? So look at there. Look at oxygen. It's smaller. It has 2 more protons in the same energy shell. So these pair of electrons are actually pulled closer to the oxygen. Nitrogen is smaller than carbon and it has 1 more proton. So it pulls this pair of electrons that make that bond, we call it covalent bond, right there. So carbon and carbon have the same attractive force. But because carbon is covalently bonded to 2 elements that are smaller, more electronegative, that's the word we use this summer to pull electrons, this guy kind of lost some electrons. It's kind of positive. And that's where the hydroxide, which is rich in electrons and very small, is going to attack that positive. And here's what it does. When we give this pair of electrons here, it kicks out this pair here. And if it kicks that pair out there, party people, what you've just done is that you have just broken that peptide bond. So hydroxides are caustic, we use the word caustic, or dangerous because they will push electrons away out of bonds as they attack something like this called the carbonyl carbon. You learn that in organic chemistry sophomore year of college. But that's important. They push electrons away, okay? And they'll break it up. So back to where I was here, okay? Back to where I was here, let's go back a little bit more. This guy, liquid Drano, okay, is dangerous to organic matter, covalent compounds, because it could attack and push electrons out of bonds. So they do it differently, but they're both dangerous. Okay, so let's get back to this. Why is it not dissolving? Well, because of the +2. Now, why is it +2? Why is magnesium so +2? Because we know that magnesium likes to lose 2 electrons. But let's consider something else here, okay? Let's bring up this chart. I love this chart. I know people are tired of it. But let's look at magnesium. It's a metal. It's big. It wants to lose 2 electrons to have a filled energy level. That's the driving force. We'll talk more about that. But as it loses 2 electrons, what happens to the size of the atom? What's that? Right, because now I still have the same number of protons, but I have 2 less what? So those remaining electrons feel the nucleus what? More. So party people, when you lose electrons, okay, here we go, here's magnesium. Here's magnesium +2. You just got smaller. What do you think that does to the charge density? Increases it. So magnesium +2, to draw this correctly, is small. And it's what? +2. So that means that the hydroxide really attracts that, and water really can't break that. Now you're really seeing what the chemistry is about. Okay, now, so I always think of it this way. If I lose weight, I get what? Smaller or bigger? Small. Okay, now, what about things that gain electrons? If I gain electron, don't I now have more electrons and protons? And they can actually pull away. You get bigger. Okay, that's why in this model, the big ion is the chlorine because it got bigger, and the small ion is the sodium. It got smaller as they became ions. Sodium plus 1, chlorine. And that's the reason why there. That's important. So, charge density. So this thing doesn't dissolve. Okay, now, what are we going to do to dissolve it? And you would say, Mr. Grodsky, is there a place I can look to see if magnesium hydroxide doesn't dissolve? Darn right you can. And I did not put it in here. Go ahead, Grodsky. There it is, table L. I'm taking L today. But look, insoluble hydroxides. Now, hydroxides are normally insoluble. Why? They are small ion. It's -1. It's their size that makes this -1 be really, really high. Now, there are some exceptions, aren't there? What's a group 1 ion? What's a group 1 ion? Okay, they're called alkali metals. Group 1 ions are over here in the first group. Lithium, sodium, potassium, rubidium. They're big because they're so big, even when they get smaller as an ion, right? They're still, because they started out big, they're still what? A big ion, which means you're stretching a +1 over a large distance, therefore they're always soluble. Okay, it's important you get that. Guess what? Am I talking about things that you haven't learned before? I'm just showing them how they all apply to this. Okay, so, party people, back to where I was. So hydroxides are normally insoluble, except when combined with group 1 ions or these guys. So party people, magnesium hydroxide is insoluble. It doesn't break apart. Why would I ever use it as an antacid? Well, let me explain. It's insoluble in water, but what if I add some acid? Which we know we're adding the protons. What is this proton going to do? H plus by hydroxide is going to make what? Water! Does water have a charge?
No.
So it's not going to stay in the crystal. So as we do what? As we neutralize the base in the crystal, okay, what's going to happen? We're going to dissolve. We're left with magnesium ions, which, by the way, is a nutrient that we need. So let's do it. So this is insoluble until I add acid, because it's the acids that are going to neutralize part of the crystal. Give that a second or two, and there might be some impurities here, but how do I know that there's going to be some dissolving? I should be able to what? See through it at some point. Give that a second, even though there's a secondary color there, okay, because of the impurity of the magnesium hydroxide I started with. At some point, you're going to start seeing me eyes through the solution. I think I see Morgandy. I think she sees my big eye. Okay? But it's gotten what? Clearer. It's got a color to it. There's an impurity in my magnesium hydroxide. But yes, there we go. Shut it down, boy. You see my big eye? Okay? That thing got clear. We dissolved it. So, I ask you, why is it a good antacid? Beautiful. Think about it. You drink this. We know hydroxides are dangerous to our what? Organic epithelial cells. We don't want to do what? Break down the cells in our esophagus. So it stays together. It doesn't react with our esophagus until it hits our stomach, where there is acid. And then that locked up crystal that didn't hurt our esophagus can do what? React with the acid and neutralize it and gently soothe your upper stomach. So it stays together as a salt that you can't do anything with as it goes to the esophagus and only reacts where the acid is. This, of course, is not what you want, because Drano, party people, would do the same thing to your stomach. It would definitely soothe your stomach. But the problem is, because it's a group 1 ion, it's soluble or insoluble? which means you got free hydroxides exposed to your esophagus, and you would basically have internal bleeding of your esophagus. So you would soothe your stomach, but you'd probably die of internal bleeding in your esophagus before that happened, okay? I don't know if that's a good trade-off. I suggest it's not. We don't ingest this. Okay, but we use it to clear our drains because it can break what? Protein bonds. Okay, we call it lye. Okay, here's the, it's not an antacid. In fact, it could be so dangerous that a lye solution, and again, I'm not trying to teach you or give you ideas here, but I want to connect you to your world. If you heat it pretty hot, it can dissolve an entire body into an oily brown liquid in just 3 hours. So people, I don't know that, I haven't tested that, but, okay, so where do they get that info? Start now! That was like 3 hours and a half, dude. It was big. No, listen. There has been a lot of this going on with people who have hid bodies and have done some heinous crimes. They have used lye, and one of the things, if you know someone is a serial killer or could be a murderer, if they have they have 50 to 100 pounds of lye in their back garage, which is sodium hydroxide, that usually is an indicator that they've done some bad things. You laugh, but that's true. In fact, it's hard to buy sodium hydroxide, okay, in large amounts now, because it's a controlled compound. But back when they were trying to identify serial killers, he's got 300 pounds of sodium hydroxide in his garage. Okay, he may have done it. Okay. Okay, so, just saying. So, any case, moving on. And in your stomach, interesting enough, this is the inside of your stomach, this is the lining. We've got these deep invaginations where we have the parietal cells to produce the hydrochloric acid. Now, why do we produce hydrochloric? To break down proteins, right? Okay, you also have pepsin. You have chief cells in here somewhere that produce pepsin that breaks down proteins and wells. But then we have these foveolar cells, and these guys produce sodium bicarb. Wait a minute, there's more things that are basic besides hydroxide. Didn't we add hydrochloric acid to carbonates in our last lab? Can you guess how many we would need here? Do you think you know what the outcome is? H2O and what?
They said they can't see carbon dioxide.
They can't see what? Ah! Am I still recording? Yeah.
That's the only recommendation.
Oh, based on my experiences.
How long have you not been able to see?
Like 3 minutes.
Okay. All right, give me a chance here. Okay, I gotta stop this.